Hello everyone, welcome to DP Tutorials by Donny Jarwa. In this teaching lesson, we will emphasize and accentuate on the application of a potentiometer. And in this section, we will be determined for the internal resistance of a cell. So in this case, we will be determining the internal resistance of a cell by using a potentiometer. Okay. So over here we have, let us recall, a potentiometer is nothing but a wire having many numbers which is fitted on a wooden board, and also keep in mind that the potentiometer works on the principle that the potential drop on the two ends of the wire is directly proportional to the length. We have done this, and over here we also have learned about the potential gradient, in which it is given by V equal KL. V equals sign KL, where this K is our potential gradient. So this is the working principle of a potentiometer wire. Let me repeat: the potentiometer, the potential across the two ends of the potentiometer wire is directly proportional to the length, okay, of the balance point. So in this case, V is proportional to L, which is equal to V equal KL. So we'll use this principle to find out what is the internal resistance of the cell. Let us explain about this circuit connection. Over here we have this potentiometer wire. This is the fast wire, okay, and starting from this endpoint, let me mark this endpoint, let me mark this first initial point as the point P, and this last terminal point as the point Q. Now we have this wire, first wire, the second wire, the third wire, the fourth wire, and the fifth wire. Now along these points P and this point Q, we will apply a potential by the hub of this battery, and we know that since this is the positive potential of the battery, this will be the negative potential of the battery. So over here, that means at point P we will apply positive potential by the hub of this voltage source, and let us initialize that. Let E be the EMF of this voltage source. Now when current is flowing through this wire, that means if we apply, if we want to measure the potential drop, or if we want to measure the null point by the help of the jockey, we can slide along the potentiometer wire by the aid of the jockey or pencil jockey. Now besides that, over here we have this key one, and also we will have this rheostat. This rheostat will help us to maintain the value of the current, or for maintaining the value of the current. Now by adjusting the value of the current from the rheostat, we can find how much current will be delivered through this circuit connection. Say, like for instance, we might apply a current say of 200. Okay, we might apply in the lab, in the physics lab, we might apply a current say of around 200 milliamperes. Okay, this amount of current which will flow through the potentiometer wire, even if we point that pencil jockey, even if we point the pencil jockey on the first wire of wheat, or if we take that pencil jockey again and point on the second wire, or if we take this pencil jockey and slide on the third wire, fourth wire, fifth wire, irrespective of the position of this pencil jockey J, the current will always be constant, and that is also one of the most important key feature of a potentiometer. In case of potentiometer, the current, okay, should be maintained constant. That is why we have to apply steady current should be supplied through the potentiometer wire in order to find the potential across the two ends of the wire. So those are some of the important points. Okay, those are some of the important points that we have learned. Okay. Now in this case, we will be determining the EMF, the internal resistance of the cell. This is the battery. If we have only two terminals, that means this is the cell. So this is the positive terminal of the cell, and this is the negative terminal of the cell. And we know that all cells will be having resistance, and that resistance of the cell is defined as what? Is defined as the internal resistance of the cell. Now we have also learned that the internal resistance of the cell is denoted by that small letter R. So we have written this resistance represented below this symbol of a cell. Let the resistance of this cell, okay, be what? Be R. Okay, let the resistance of that cell be R. And in this case, that means this circuit is apart from this main circuit. This circuit which is connected away or from the main circuit, this is what is known in the lab as the auxiliary circuit. Okay? This is known as the auxiliary circuit. This is known as the auxiliary circuit. Okay? So this we will connect across this end of the wire. We will connect across this end of the wire so that we can find the potential. Okay, we will find the potential. Then in this case, let us connect. Okay, let us connect this auxiliary circuit along this along the positive terminal of the battery, or if we don't connect across the positive terminal of the battery, we will connect this auxiliary circuit to the first entry of this first wire. This will be what? This will be our first wire. Okay? This is what we call as the first wire. So we will connect that. We will connect this auxiliary circuit across this first entry of the first wire, which means that this will be at a positive potential. Okay? This will be at a positive potential. And then on this auxiliary circuit, we have this shunt resistance. What is this shunt resistance? Basically, shunt resistance is nothing but a resistance which is connected in parallel. What is a shunt resistance? A shunt resistance is nothing but a resistance box, okay, which is connected in parallel to a battery or to a cell. Okay, to a battery or to a cell. That is the purpose of a shunt. Okay, by using a shunt resistance, that means we will increase the potential of the circuit, okay, or we increase the sensitivity of the circuit. Now over here we have another resistance box, and we will have a galvanometer. This will be the circuit arrangement. And from here, suppose over here we have these two keys, key 1 and key 2, and we will also have a pencil jockey for finding the null point. Okay, for finding the null point. Now, if we don't close, if we insert this key, okay, if we insert the plug from the key K1, or when the key K1 is closed, okay, when the key K1 is closed, we find that current will be flowing on that circuit. So if or when key K1 is closed, and in this case key 2 is open, so we will open. So we will not insert any plug on key 2. So that is why key 2 is open. When K1 is closed and K2 is open, the potential drop, okay, this potential drop, not this will be potent, this potential drop or potential difference across the potentiometer, okay, the potential difference is developed across the potentiometer, and the current starts flowing through it. So from here, that means this current will start flowing across the potentiometer wire, okay, across all points. Okay, from here will move on this direction, from here will move on this direction. Okay, all these will be the direction of the current flow, and then we will have some deflection. Okay, some deflection on the ammeter. Okay, then what happens is that this current is adjusted with the help of a rheostat. This I have explained, and we can maintain. We will get steady current simply by adjusting the value of the current from the rheostat. Okay, so from here, now when you take this jockey, when you take that jockey J and then slide along the potentiometer wire, you'll find out some null points. See, this is the jockey J, and when you slide this jockey J, when the jockey J is slided along the potentiometer wire, then what will happen on this galvanometer? Okay, on that galvanometer, the galvanometer is symbol in this form. That means we have 0 degree, we have what? We have 30 degree, and we also have 30 degree. That indicator, okay, that indicator will, if you want to get Null point, that means that indicator, suppose for instance it deflects in this direction, it deflects in this direction, but if you want to get null point, that means the needle should point at what? Should point at 0, if this is your galvanometer. So by sliding this jockey, we want to get null point on the potentiometer wire. So that will correspond to what? That will correspond to 0° deflection on the galvanometer. When that is obtained, that means you have determined the EMF E of the cell in terms of the length. So from here, there will be some length from this point up to this point. The length might be 100 cm from this point up to this point. Suppose the length is 50. So total length of the first wire and of the second wire, where you obtain the null point, where you obtain this 0 deflection. Suppose the total length will be what? Suppose let me name that as L1. L1 in this case, in that case, will be how much? Will be equal to, suppose 150 centimeters. Okay? 150 centimeters. So over here, if the null point is obtained at a distance, say in general, let me take that distance as L1. If the distance is obtained at a distance, if the null point is obtained at a distance L1 from this point P, then the EMF is given by 1. This EMF E of this battery is directly proportional to the length L1. Okay, based from this one, from this working principle of a potentiometer. So from here, which means that this EMF E will be equal to 1, will be equal to K times L1. So what is this K? Our K in this case is nothing but the potential gradient. Okay, this K is our potential gradient. So this K is our potential gradient. Okay, K is your potential gradient. The SI unit of potential gradient is voltage per meter. So this K is your potential gradient. Now over here, okay, we will mark that as equation number 1. And then next, firstly, we have closed this key 1 and current is moving on the circuit, and this key 2 is 1. This key 2 is open. Now next case, we will close the circuit by inserting this plug on the key K2. So when you insert this plug on the key K2, then you will determine the voltage, okay, the voltage V of this cell. So from here, when the shunt resistance R is inserted, this is your shunt resistance, and now when the key K2, okay, when that key K2 is closed, then you have to again find the null point on the wire. If the null point is obtained, say, suppose with respect to that shunt resistance, say you might obtain the null point, suppose at this point. This will be by placing the key K1, and this is the null point, the position of the jockey, by closing this jockey K2, say at that particular point. Then the distance or the balance length will be different. So in this case, if the null point is obtained, say at this distance J2, which I will write as L2, from this point P, you obtain this distance J2 from P at the distance L2. Then the potential difference across the resistance box, okay, the potential difference across this resistance box is given by what? Is given by V. This will be directly proportional to 1. This will be directly proportional to L2, which in this case, this V will be equal to 1. This V will be equal to K into L2. Potential gradient for a potentiometer will always be the same. You will not have K1, you will not have K2. So let us mark this as equation number 2. Now, in this case, if we divide, suppose if we take equation 1 divided by equation 2, we will get some relation. Okay, so this will be left hand side of 1 divided by left hand side of 2. This will be equal to 1. This will be equal to K L1 divided by K L2, which means that this ratio of EMF of the cell divided by EMF of the EMF of the battery divided by EMF of the cell, this will be equal to 1. This will be equal to L1 divided by L2. Okay. So from here, then if we want to find out the internal resistance of the cell, that means from here, we will make some consideration. If R be the internal resistance of the cell and capital R be the resistance of this resistance box, this is capital R as the resistance of the resistance box, then the relation between the EMF of the cell and the terminal potential difference is given by. So let me recall some ideas about EMF of the cell and terminal potential difference of the cell. The EMF of the cell is nothing but the voltage or potential of the cell in an open circuit, and that terminal potential difference, the terminal potential difference, or I can write in short as TPD, the terminal potential difference of the cell is the potential difference of the cell in a closed circuit. We have also learned that the EMF of the cell is always more than the terminal potential difference of the cell. We have also come across that the current through the cell is given by this relation, EMF of the cell divided by the total resistance of the cell, which if capital R is the load resistance and R is your internal resistance, then from here you will get some relation of I capital R into I small r, this will be equal to 1, this will be equal to E. So from here we can arrive at a condition that this small IR will be equal to 1, E minus capital IR, E minus E minus capital IR. So this will be equal to E, and this will be equal to minus capital IR. So if you want to find out R, that means this will be E. From Ohm's law, capital IR is nothing but what? Capital IR is nothing but the voltage. Okay, and then when we cross multiply this I this side, then you will get this relation. So we will use, this is the expression for what? This is the expression for the relation between the EMF of the cell and the terminal potential difference, which we have derived in the previous section. So you can review this video clip concerning this derivation. So from here I will just use this result in order to write the relation, in order to find out what is the internal resistance of the cell. So from here, what is that relation? Over here, this will be the internal resistance of the cell is given by this relation, E minus V divided by 1, divided by I. We also know, from Ohm's law, that V equal 1, that V is equal to IR. V is equal to IR. V will be equal to IR. V will be equal to IR. V equal IR. Then from here we can rewrite this equation in another form. We can write E minus V in place of this I. In place of that I, we can substitute. So over here, if we write 1 divided by I, this will be equal to 1. This will be equal to V divided by R divided by V. R divided by V. We can do some relevant cross multiplication. Cross multiply I this side and cross multiply V this side, then you'll get this result. Then from here, this I we can write by what? We can write by this relation, which is equal to V into R. So from here, again, if we try to solve again, that means over here this will be E divided by V minus 1 into R. So from here, this is another form for finding the internal resistance of the cell. If you know the EMF of the cell, if you know the EMF E of the cell, and if you know the terminal potential difference V of the cell. But if you're using the potentiometer wire, that means we already know this ratio of E by V from this result, then that E by V will be equal to what? Will be equal to L1 divided by L2. L1 divided by L2 minus 1 into R. That will be the relation, how to find out the internal resistance R of the cell. In order to find out the resistance R of the cell. So from here, if finding this, we should know that the units over here, the units for this internal resistance will be ohms. Why is it ohms? Because over here centimeter divided by centimeter, we will get cancelled. So we'll get the resistance recorded in ohms. But keep in mind that over here in this case, the value of L1 should always be more than the value of L2, which means that the balance length corresponding to the battery should always be more than the balance length corresponding to the cell. Okay, so that you will get value, so that this right hand side will be positive. Okay, so just go back and review all these discussions which I have done. In the examination time, remember that you need not derive all this from all this. There's a relationship between terminal potential difference of the cell and EMF of the cell, but you need to only use this result. Yeah. So until next time, thank you.